Hello everyone and welcome to today's lecture on expressions and assignment statements. Before we dive in, let's take a moment to understand why this topic is important. Um, so, so in this session, we'll focus on an essential aspect and expressions and assignment statements form the core of how programming languages execute computations and store values. Whether we are working with C, Java, Python, or any other language, understanding these concepts is fundamental to writing efficient and structured code. So, by the end of this session, you should have a deeper understanding of how expressions work and how assignment statements influence program behavior. So, first of all, we'll explore key concepts that dictate how expressions are evaluated and processed in various programming languages. Specifically, we'll cover overloaded operators, type conversions, relation and Boolean expressions, short circuit evaluations, assignment statements, and mixed mode assignment. So here, first of all, what is expressions? So expressions form the backbone of any programming language, allowing us to perform calculations, make logical decisions, and manipulate data. Whether you are coding in any language, understanding expressions is essential for writing efficient and error-free programs. So here to understand expression evolution, we need to be familiar with the orders of operator and operand evolution. So here, okay, now that we have introduced the significance of expressions in programming, let's learn about arithmetic expressions. So arithmetic evolution was one of the primary motivations behind the development of early programming languages. Before graphical interfaces and complex algorithms, programming was fundamentally about performing calculations efficiently. Now, an arithmetic expression consists of operators, which are symbols that define the operations like plus, minus, multiplications. Then operands, which is the value on which the operations are performed. Third is parentheses and function calls. So which is used to control the order of evolution. Now we categorize operators based on the number of operands they require. First, we have unary operators where we have one operand. Then we have binary operators where we have two operands. And then third, we have ternary operators where we have three operands. So we'll also see the examples of these operators. Okay, now we'll see, now that we understand arithmetic expressions, let's see what is actually unary arithmetic operators in programming languages like C, C++, and Java. Now, as I said, unary operators operate on a single operand and are commonly used in mathematical expressions. The two most fundamental unary operators are unary plus and unary minus. Now, on unary plus, which is plus A, That means in C and C++, the unary plus operator has no effect on its operand. It is often used um, for code clarity but does not alter the value. In Java, however, it has a specific use case. So, if applied to character, short, or byte data types, it automatically converts them to an integer. Otherwise, like in C++, it has no effect. So, keep that in mind. If you are using depending on the type of programming languages, some functions or some operators have different functions, different type of usability. So as I said, like in C or C++, it has no effect, but in Java, it automatically applies when you apply it to character, short, or byte data type. It automatically converts them to an integer. For example, if you write plus num divided by 5, so these are the examples. Now, unary minus. This operator negates the value of its operand. It is used to convert positive values to negative and vice versa. So these are the examples we have: minus num by 5. So this is how we can write that operator. These operators play a key role in computations and are frequently used in mathematical and logical expressions. Okay, building on our discussion of unary arithmetic operators, let's now focus on increment and decrement operators. So, these operators are frequently used in loops, counters, and various programming constructs to modify variable values efficiently. Now, there are two types of increment and decrements: pre-increment and decrement, and post-increment and decrement. So, let's examine the differences. Okay, now here, if we talk about pre-increment, which is written by plus plus a, so the variable is incremented first, then used in the expression. So if for example, if you write a equal to 5 and b equal to plus plus a, then a is first incremented and then it will be used. Second, we have post increment, a plus plus. In this case, the variable is used first and then incremented. Now here, for example, if we say integer a equal to 5 and then b equal to a plus plus, first b is assigned 5, then it will increment by 1. Third, we have pre-decrement. On p-decrement, we have minus minus a. So the variable is decremented first, then used in the expression, same way we did before. Then similarly, post-decrement, the variable is used first, then decremented. Okay, now that we have covered unary operators, let's move to binary or arithmetic operators, which are the most commonly used operators in programming. These operators take two operands and perform mathematical operations such as addition, subtraction, multiplication, division, and modulus. The table on this slide provides an overview of how binary arithmetic operators behave in C and C++ and also in Java. So here, let's go through each operation. First of all, addition. So these are the example: a plus b. If both operands are integers, the result is an integer. If one operand is a floating point number, the result is a double precision floating point value. So here we have automatic type conversion. Second, we have subtraction. A minus B. It works similarly to addition. Integer minus integer results in an integer. But if one operand is a floating point value, the result is floating point value. Third is multiplication. A multiply B follows the same rule, but if one operand is floating point number, the result is prompt to floating point. Then division. Here the operator behaves differently in C or C++ and Java when dealing with integers. Now in C and Java, integer division discards the decimal point, like the decimal part. So if at least one operand is a floating point number, the result retains decimal precision. So for example, if you have integer x equal to 5 and y equal to 2, if we have double result 1 equal to x by y and double result 2 equal to double x by y. Now here on the first one, the result will be 2, the integer division, but on the second one the result will be 2.5, which is explicit typecasting. Okay, now fifth is modulus, which is the remainder operator. It returns the remainder after division. It works only for integer values. So here there is no chance for floating point remainder or anything. It has to be integer. Okay, so some key takeaways we can say from this table, like integer operations remain integers except for division, which discards decimals unless converted. Second, we can say that floating point promotion occurs when one operand is not an integer. Then third is the modulus operator is useful for tasks like checking even odd numbers and cyclic calculations. Okay, now we'll explore ternary operator. This operator allows us to write conditional expressions in a more compact form than using traditional if-else statement. Now, understanding the ternary operator. So the ternary operator is the only operator in C and C++ and Java that takes 3 operands. So if its syntax follows this pattern, like condition, question mark, expression if true, colon, expression if false, semicolon. This is how it is. Now if the condition evaluates to true, the first expression is executed. Otherwise, the second expression is executed. Now here we have an example. We have average, which is equal to count equal to 0, question mark 0, colon, sum by count. So this expression is equivalent to if count equal to 0, average equal to 0, else average equal to sum by count. So if you use the if-else condition, this expression is equivalent to this line. Now here if count is 0, the expression evaluates to 0. Otherwise, sum divided by count is assigned to average. Now both approaches achieve the same result, but the ternary operator is more compact and often preferred for simpler conditional expressions. And it reduces the number of lines of code and enhances readability for simple conditions, and which is commonly used for inline decisions in expressions. However, for complex conditions, traditional if-else statements are often preferred for better clarity and maintainability. So now that we have covered various arithmetic operators, let's discuss operator precedence rules. which determine the order in which operations are evaluated in an expression. So, operator precedence is crucial because it ensures expressions are executed in the correct sequence, preventing unexpected results. Programming languages follow a predefined hierarchy of operations similar to the mathematical order of operations like parentheses, exponents, multiplication, division, addition, subtraction. So here we have some typical operator precedence. We have parentheses like highest precedence, ensuring specific operations are evaluated first. Then unary operators, plus minus, plus plus, minus minus, these execute before any binary operations. Third is exponentiation. If supported, like in Python, it executes before multiplication and division. Then multiplication, division, modulus, these have the same precedence and are evaluated left to right. Then lastly, addition and subtraction. These are the lowest precedent among arithmetic operators. Now, operators with higher precedence are evaluated first, as I said, and operators at the same precedent level follow left to right associatively, except for exponentiation, which is right to left in some languages. And parentheses override precedence, like allowing us to control the order of operations explicitly. So let's move on to another important concept, which is operator associativity. This defines how operators of the same precedence level are grouped in an expression. This is particularly important when multiple operators appear in the same statement without parentheses. For example, like we have left to right associatively, most common. This is most common, like most operators follow left to right associativity. This means that when multiple operators of the same precedence appear, they are evaluated from left to right. So if, for example, we have integer result equal to 10 minus 5 minus 2, so it will be evaluated as 10 minus 5 first, then whatever is the result, which will be 10 minus 5 is 5, then from 5 2 will be subtracted, so the final result is 3. So it will be evaluated from left to right. Then if we have right to left associatively, which is rare some cases, it is for like exponentiation, star 2 star in Python, and assignment operators. These follows this right to left associativity. This means evolution happens from right to left. Then we have APL, which is right to left associatively for all operators. Like in the APL programming language, all operators have the same precedence and follow right to left associativity. This is an uncommon rule in most modern programming languages. Okay, now let's turn our focus to conditional expressions, which allow us to make decisions within a single line of code. This is especially useful for writing concise, readable logic without using a full if-else block. So for example, if I write average equal to count equal to 0, question mark 0, colon, sum by count. So this expression uses the ternary operator, which evaluates a condition and returns one of two values. If count is equal to 0 is true, average is assigned 0. If the condition is false, average is assigned the result of sum by count. So this is equivalent to this if else, like normal regular if else conditions, but both approaches produce the same result. The ternary version, however, is much more compact and is ideal for simple decision making in expressions, and they help reduce code length, improve readability when conditions are straightforward. But however, it's important to remember that overusing the ternary operator in complex conditions can make the code hard to read and maintain. Now let's explore another topic, which is operand evolution order. Um, so if you look at the example here, y is equal to fun x plus x. We are combining two operands, fun x and x. But here's the catch. Which one gets evaluated first? In many programming languages, especially C and C++, the order of operand evolution is not guaranteed. This can lead to unpredictable results if one of the operands has a side effect, a situation where a function changes the value of a variable or parameter. So, what is the side effect? Now, a side effect occurs when evaluating an expression does more than just return a value. It might modify a global variable, or it might change a parameter's value, or it can also alter program state in some way. So, let's say fun x increments x before returning a result, depending on the compiler or optimization setting. The order in which fun x and x are evaluated may change. So we'll now see some example to better understand operand evolution and side effects. Now let's walk through this functional side effect example in C++. So we have integer a equal to 5, then we have integer function 1 and main function. Now at first glance you might expect the output to be 5 plus 3 equal to 10, because we have the code written like that. But let's analyze the behavior more closely. So what's happening? Initially a was equal to 5. Now on second line, when we have function 1 which modifies it to a to 17 and returns 3. So on function 1 we are modifying the value of a to 17 and it returned 3. Then on third line, the expression inside the main function, the expression a equal to a plus fun 1, it becomes the problematic due to evolution order. Now here's the catch. If a is read first as 5 before function 1 executes, then you get a equal to 5 plus 3, which is 8. But if function 1 runs first, it changes a to 17 and you have a equal to 17 plus 3, which is equal to 20. But in this case the output is 8. Why? Because in this specific compiler's evaluation strategy, the value of a is read first before function 1 is executed. Now then function 1 sets a equal to 17, but the original value 5 is still used in the addition. So a equal to 5 plus 3, and finally a equal to 8. So this example clearly demonstrates how side effects combined with unspecified evolution order can lead to unpredictable behavior. Okay, now here's the example 2. So here in this example, this time we slightly rearranged the operands, but the outcome is different. Now in this example, the function of f fun1 is called before accessing the value of a. Then in the expression a equal to function 1 plus a, we are now adding the return value of function 1, which is 3, and then the new value of a, which was changed to 17 inside function 1. Now that's why our result is now a equal to 3 plus 17, which is equal to 20. Now, even though the code looks very similar to the previous example, changing the operand order completely changes the result. But why? Because of the timing of the side effect caused by the function call. And this illustrates how evolution order can impact results, especially when variables are modified during function execution. Okay, now let's explore the concept of overloaded operators, a powerful feature in some programming languages that enhances readability and expressiveness. Now, what is operator overloading? Operator overloading allows developers to customize the behavior of standard operators like plus, minus, multiplication, etc. for user defined data types. Now in other words, we can say you can define what an operator should do when it is used with objects of a class. So in C++, operator overloading is widely used to work with objects like complex numbers, vectors, matrices, and more. And also in Fortran 95 and ADA, these languages also support operator overloading. You can make your code behave more like built-in types by redefining how operators work for your custom classes. Java does not support operator overloading. The language designers chose to avoid it to maintain simplicity and prevent confusion that can arise from misuse. Now let's talk about type conversions, a very common and important concept in programming languages, especially when working with mixed data types in expressions. Type conversions happen when a value of one data type is automatically or explicitly converted into another. This process is critical to ensure compatibility and correctness during computation. Now, so if we try to narrow the conversion, so first of all, it converts a value to a smaller or less precise data type. This type of conversion may result in data loss. So for example, if we have float pi, the value of pi is 3.14. Now if we make it integer, so if we say integer x equal to integer pi, which where x becomes 3, the functional part is lost. So these conversions usually require explicit casting in most languages to avoid accidental data loss. Now, and then second is widening conversion. So it converts a value to a larger or more precise data type. Now this conversion is safe because the target type can hold all possible values of the original type. So for example, if we have integer a equal to 42 and we want to convert it into float, so we can say float b equal to a. Now it is widening but no data is lost. Now type conversions affect how arithmetic expressions are evaluated. Okay, now let's break down two fundamental types of type conversions, implicit and explicit. So on implicit conversion, this is an automatic conversion performed by the compiler. So it happens when two different data types are involved in an expression and one is promoted to match the other. Um, so basically, if for example you say integer a equal to 5 and then you say float b equal to a plus 2.5, so a is implicitly converted to float. Now this convention this conversion is convenient, but sometimes risky if it causes unexpected data promotions or loss of precision. So next we have explicit conversion, which is basically casting. This is manual conversion done by the programmer using typecasting syntax. It is useful when you want full control over how data is converted. So in this case, if you, for example, if you say float pi equal to 3.14 and integer x equal to integer pi, now your explicit cast truncates decimal. In this case, you are clearly telling the compiler, I know this might cause a loss of data, but I'm okay with it. So it is basically casting it and making it 3 only. So the value of x will be 3 instead of 3.14. Now the key differences are like on implicit the compiler decides, which is automatic but can be risky, and on explicit you decide, means the programmer decide, which is manual and safe if used carefully. So there is an example of explicit type conversions. So let's continue our discussion on type conversion by looking at a practical example. So this is basically typecasting. Like we have two integer a and b, then we have float a. Now if we say if x equal to float a by float b, so we are doing typecasting. Now normally if you divide two integers in C or C++, the result will be integer division, which means any decimal portion is truncated. But in this case, both b and b are explicitly cast to float before division. Now this tells the compiler convert both operands to floating point first, then do the division. Now as a result, the division is floating point division and the result is stored in a float variable x. Okay, now that we've discussed how type conversions work, both implicit and explicit, it's important to also understand the risks and potential errors that can occur during these conversions. Now first, what I said also before, like if you're narrowing down the conversion, so this happens when you are making it like sometimes when you're making from float to integer, you may lose some data. So if the original value can be represented accurately, you might get truncated or incorrect results. Now second is overflow and underflow errors. So overflow occurs when a value exceeds the maximum that a data type can hold, and underflow occurs when a value is too small to be represented accurately, often with floats. Like if you say short a equal to 32767, if you want to say like a equal to a plus 1 and wraps around resulting in a negative value, so that is an error here. Third is like exception handling in some languages, languages like ADA, C++, and Java offer mechanisms to catch and handle conversion errors. Like in Java, you might get a number format exception if string to number conversion fails. In C++, which allows exception handling using try-catch blocks, in more advanced scenarios. ADA has a strict range checking built in, which makes it more robust for preventing conversion errors. Okay, now let's look at relational and Boolean expressions, which are crucial for making decisions and controlling the flow of logic in programming. Now, here we have relational operators. So, relational operators are used to compare two values. The result of a relational expression is always a Boolean value, either true or false. Now, in ADA language, we have equals, not equals, greater than, less than, or like greater than or equal to, and less than or equal to. In Java and also in C and C++, we have equals, not equal, same meanings as in ADA. So these are used in conditional structures like if, while, and for. Then on Boolean operators like it is a combine of true false values using logical operators. They allow us to create compound conditions like in C and C++, we have and, like this is logical and, true only if both operands are true. Then we have logical or, it is true if at least one operand is true. Then we have logical not, like it reverses the truth value of its operand. Okay, now as we continue our discussion on Boolean logic, it's important to highlight how C handles Boolean values, which is slightly different from other modern languages like Java or Python. Now, C does not have a native Boolean data type in its original specification. Instead, it uses integers to represent Boolean values, like 0 is treated as false and any non-zero value is treated as true. Like in modern C, like C99 and later, starting with C99, a Boolean, like a bool type and a standard bool.h header were introduced. But even with stdbool with header file under the hood, the Boolean values are still represented using integers 0 and 1. Okay, now let's see in an important concept in Boolean logic, short circuit evaluation. Now, what is short circuit evaluation? It is a technique used by programming languages to optimize the evaluation of logical expressions by skipping unnecessary conditions. Like it works with logical and logical or operations. Now, if we say, we have an example here, so a greater than or equal to 0 and b less than 10. This is our condition. Now, in this condition, if a is less than 0, the first part of the condition is false. Since an AND operation requires both sides to be true, the program doesn't bother checking b less than 10 or not. That's short circuiting in action. It saves time by not evaluating the second condition if the outcome is already determined. Now, why it matters? Like it saves computational efforts, like especially if the second condition is expensive. Also, it can protect against issues like division by zero or null pointer access. So, short circuiting helps prevent unnecessary or unsafe operations. Without it, your code could cause runtime errors like accessing memory out of bounds or dereferencing null points. For example, here if you look at this, while index is less than listen and list index, list length and list index is not equal to key and index plus plus. Here how it works: this loop is searching through an array list for a key. Now first condition checks if index is still within bounds of the list. Then the second condition checks if the current element is equal to the key. Now thanks to short circuit evaluation, if index is not less than list length, the second condition is skipped. Now this prevents the program from doing list index, which would be an out of bounds access, a major bug. Now if both conditions were always evaluated, list index would be accessed even when index is greater or equal to list length, causing a crash or undefined variable or behavior. Now here let's look another example here. Now by looking at how it interacts with side effects, those subtle changes in program state that happen when expressions are evaluated. So for example here, if a greater than b or b plus plus division by 3. Now here what's happening, the first condition is true. If the first condition is true, the second expression b plus plus by 3 is never evaluated. Now that means the b plus plus side effect does not happen. Now this is the essence of short circuiting. We avoid evaluating the second part of an OR condition if the first part is already true. Now why this matter? Now side effects like b plus plus can be missed if the expression is short circuited. If your logic depends on that side effect, you might get unexpected behavior. So don't place critical updates or state changes inside a condition that might be skipped. Now in ADA, it uses and then and or else to explicitly indicate short circuiting. This makes the logic very clear and intentional, like and then short circuit and or else short circuit or. Okay, now let's move on to a fundamental part of every programming languages, like assignment statements. It is how we store values in variables, update them, and drive the logic of a program forward it. So it connects computation with memory. So for general syntax, we have target value, variable, assignment operator, and expression. This is the general syntax. Now the expression is evaluated first and its result is stored in the target variable. The assignment operator defines how that value is stored, usually as a direct replacement. Now equal to the assignment operator in C, Java, and most modern languages. This is the most commonly used operator for assignment. Equal sign. Now in Pascal, ADA, or Algol, we have this kind of sign, colon, and then as equal. These languages use this type to make a clear distinction between assignment and comparison. Like it helps avoid confusion between assigning a value and checking for equality. So there's an important note to understand that assignment is not the same as equality. Equal means the equal sign means store the result in the variable, not check if two values are equal. Now some languages like C allow chaining assignments like x equal to x equal to y equal to z or equal to 0. This sets all three variables is equal to 0, evaluated from right to left. Okay, now let's look at two useful variations of assignment in programming, like multiple assignment and conditional assignment. Multiple assignment is chained assignment. This feature allows you to assign the same value to multiple variables in a single line. Now we just saw it in our previous slide. Like in C, you can write sum equal to total equal to 0. That means the expression on the right 0 is evaluated first, then it's assigned to total. The result of that assignment, which is still 0, is then assigned to sum. Now this is often used for initializing multiple variables with the same value at once. Second, we have conditional assignment using the ternary operator. Like you can also assign values based on a condition using the ternary operator, like that we saw before, the ternary operator, question mark and colon. So we can have flag count 1, count 2 equal to 0. You can also write it like that. Here's what this means. If flag is true, count 1 is 0 is executed. If flag is false, count 2 is 0 is executed. Now this specific syntax may vary across languages. In some, this form isn't valid unless wrapped in parentheses. For instance, in C++, you have to write it inside a parenthesis. Okay, now let's take a moment to revisit unary assignment operators, which are not only used for incrementing and decrementing but also for performing quick updates to variable inside our expressions. So two forms of increment. Post increment, the variable is used first, then incremented. Then pre-increment, the variable is incremented first, then used. So the key takeaways here, like to understand when you're using the value versus when you're modifying it, and to avoid using increment decrement inside complex expressions if it might reduce clarity. Readability is key. So finally, let's wrap up our session with mixed mode assignment, which deals with assigning values where different data types are involved. So what is mixed mode assignment? Mixed mode assignments happen when the data types of the variables and expressions don't match, and a type conversion must occur for the assignment to happen. So here is an example, like integer ab, float c equal to a by b. Now in this case, a and b are integers, but the result is being assigned to a float c. Now since both operands a and b are integers, the division is done as integer division, and only then the result is converted to float. Now to fix this, at least one of the operands should be explicitly cast to float. Now here we can write c equal to float a by b. Now in Java only allows widening conversions in assignments. You can assign an integer to a float but not a float to an integer without explicit casting. And in ADA, it does not allow assignment this operation. It requires explicit conversion. No silent type conversion or type promotion happens. Now that brings us to the end of our lecture on arithmetic expression and assignment operators. So if you have any question, feel free to email me or post it on our group discussion forum. So that's all for today. Thank you.